Hello everyone. So this is an extra video on more example on divergent theorem. So let's quickly review about divergent theorem. So idea is that, okay, if a surface is closed surface and f is defined on the region that the surface bounded, then we can use the divergent theorem, transform the double integral of the vector field surface integral into a triple integral, a usual function way. So last time we do a lot of calculation like this. Like using the direct way is ugly, doable, but ugly, I already type it. And we can use divergent theorem, will be way quicker, And also we have like, you have multiple surfaces, then we can do this, then we can do this as well. And so now we just add one more thing. So sometimes we can have, if the surface is not closed, but if you want to use divergent theorem, we can add an extra surface to make that a closed surface. Then we can use divergent theorem. So the one important idea of this, we already did this, we already did this, we also did this. We add an extra surface to make it a closed surface. Then it will be doable. And one of the most important thing is this kind of thing. So now, also, this is the flux of this guy. So again, this is a vector field, and S is whatever surface is container 0, 0, 0. But even though that is a closed surface, it's a closed surface. But now F is not defined as 0, 0, 0. So what we can do, we circle out something in the middle, and we scoop that out, and the remaining region, the yellow one, we can use, in this case, we can happily use divergent theorem. So that's the idea. So we can use idea, we can use divergent theorem. Oh, I already wrote it. I want to use divergent theorem on E minus E star. Okay, so that's it. So the whole surface is S, and we scoop out, maybe we'll say this is S star. This is S star. Okay, so we can use divergence on this one. So we just directly write this. So boundary, the divergent theorem tells us that the boundary of E star F ds will equal the triple integral divergent theorem, divergent F, this is E star dV. That's it. We can use divergent theorem on this one. But be careful again. If we want this whole thing, divergent theorem is outward normal. So if we scoop one thing out, if we want the whole yellow region, this whole yellow region be outward normal, this S star has to be pointing inward. That's the idea. So let's do the calculation. So first, f of this guy is ugly, but we already did that if you remember, in the vector field class. So divergent f, where f is this guy, is negative, what I don't remember, negative xyz. It's negative xyz. And denominator is x squared plus y squared plus z squared power 3 over 2. So divergent f, if we really want to do the calculation, we just do it term by term. So in this case, divergent f, this will be PQR, right? Where P is this guy, negative x squared plus y squared plus z squared, 3 over 2. What about we just do one? We'll just do one, and we'll see what happened. Okay? So Px, in this case, we will have to use the quotient rule. Since now both of them, the numerator and denominator, all have x. So quotient gives us this guy will be x squared plus y squared plus z squared to the power 3. And this is negative 1, x squared plus y squared plus z squared, 3 over 2. And minus, keep the original 1, and this is 3 over 2, x squared, y squared, z squared times 2x. So this is quotient rule. So that's it. So if we do the calculation, it will look like this. X squared plus y squared plus z squared, this is power 3. And this is plus plus become minus minus become plus. 2 goes away. So negative 2. So this way will become negative x squared plus y squared plus z squared 3 over 2 and plus 3x squared x squared plus y squared plus z squared. So this look okay. This look okay. Oh, sorry. This should be and one quotient rule. This will be 2/3 negative. That'll be 1/2, 1/2, 1/2 quotient rule. Quotient rule. Okay. But when you look at this, when you do x, the only thing is negative x here, right? So if we do y, like this is y, sorry, if we do qy, this will become y, this will just become 2y. So you might guess this is just y. So we can guess that, okay, they are all of the similar form. So qy will also become this guy, x squared, y squared, z squared, power 3, negative x squared, y squared, plus z squared, power 3 over 2, and plus 3y squared, x squared, plus y squared, plus z squared, 1/2. And qz and rz will be the same thing. It's basically just quotient rule, ugly quotient rule, but doable. So divergent f will be sum of them. So this will be the numerator, the denominator, everyone has the same thing. And we have negative 3 x squared plus y squared z squared 3 over 2. And now we have plus 3 x squared plus y squared plus z squared. And x squared plus y squared plus z squared 1/2. And by exponent is 1 plus 1/2 is 3 over 2. So 3 minus 3 goes away. So divergence is 0. Yay. Ugly but doable, but doable, but doable. Ugly but doable. So now we have the divergence go to 0. Divergence go to 0. So we have this. This will go to 0. This will go to 0. So again, we have this boundary of E star FDS. Remember, boundary of E star is now two things. It's S and S star. It's S and S star. So it becomes S FDS and plus S star FDS. So equals 0 by divergence theorem. So now the desired one will be this guy. S FDS will become negative S star FDS. Yay, we're really close. But again, this S star is inner normal. So if we have a negative 1, it will just be negative inner normal will just be outer normal. Will just be outer normal. So this is good. So this is good. So finally we'll have S FDS will be as negative S star FDS. And this will just be usual outer normal. So we can just do the calculation. We can just do the calculation. So the calculation is okay. Since F it look like that. So remember ds is the normal dot ds. And we note that for the circle of radius r, the normal, trust me a little bit, trust me a little bit, trust me a little bit. We already did that in class, but I hope you can trust me here now. Normal will be 1 over r and r. R is the radius. R is the radius. You can do the spherical coordinate and do the computation yourself, but trust me here. So an f, we already have this, is negative xyz. And this is x squared plus y squared, z squared, 3 over 2. And if we did x squared plus z squared, it's on the inner sphere. So we did x squared plus y squared plus z squared equals r squared. So this will be negative r, and this is just r to the 3 over 2. That's it. That's it. Oh, r2 to the 3 over 2, so it's r to the power 3. So finally, this guy this guy would just be using the spherical coordinate, so we don't care about that. So this is S star, negative S star, and this is just negative X, Y, Z, R to the power 3, dot 1 over R, R. Maybe I'll just keep the R, so this will be R, R, and this R, and dA, right? And so this is a constant. This is a constant, is R to the power 4, R to the power, R to the power 4. But be careful, we also have this, R dot R will be R squared. So in this case, R satisfy equals R, so this is R squared. So this is R squared. So finally, the answer of this part would just be 1 over R squared, and this is negative S star dA. This guy. S star dA. So remember, if we have S star dA, this is just the surface area of S star, negative S star. But negative S star and S star, they share the same surface area, so we don't have to care about the normal orientation now. So it's just a purely surface stuff. It's just a purely surface stuff. So finally, we can have, if you remember, the surface area of the circle is 4 pi r squared. So finally, this answer will just be 1 over r squared times 4 pi r squared goes away. So it'll be 4 pi. Yay! So, oh, sorry, negative 4 pi, since we have a negative sign outside, negative 4 pi, negative 4 pi, negative 4 pi. So that's the really important example. If we scoop out something, then we can also try to use the divergence theorem. It's just the calculation a little bit hard. And I want to say something more. This 4 pi is actually pretty common in physics. If you remember, if this guy, remark, if F look like this, like negative R, this is R to the power 3 over 2, right? To the power 3. This is basically what we have. This is, if you remember this is R to the power 3. This is just the, okay, maybe I write this. Maybe you recognize this. 1 over R squared and times the unit vector R over R. So this is just what we have is the inverse square law, right? Inverse square law. So for gravitational force, electricity force, like magnetic force, we all satisfied this. So if you remember, Coulomb field look like this: F equals Q over 4 pi epsilon 0 R to the power 3. Why do we need this 4 pi? Since every time, if we calculate the electric of this charge, we'll face this problem. We'll always have this 4 pi pop out. So we divide by this 4 pi. You might wonder, okay, this is a constant. Why do we have to write a 4 pi? That's the reason. Since every time we calculate the field, the force or something, we'll have an extra 4 pi. We'll have an extra 4 pi by the divergence theorem. So we need to always divide by that out. And that's it. So I hope you, since most of you will have some physics in the future or in engineering, you'll see this a lot. Why? This is a quick question. Like, why don't we just leave the constant c? Why we have to specify 4 pi out? Since every time if we don't have the 4 pi out, we accumulate the 4 pi again and again. So we always have to divide it out. And that's the reason. So this 4 pi is just indicator that, okay, without nothing, there's a 4 pi. And that's it. So you'll see that in electromagnetic and your gravitational force. And this will also have a lot of calculation. I already put some in the handout. And that's all for this video. I'll see you in the next video.